Hey everyone, it's nice to be here and thank you for this opportunity, Nisha. My name is Vishakha Gupta and I'm the co-founder and CEO of ApertureData. We want to focus our talk today on data management, particularly on visual data, and I want to start by explaining why. Remis, who is our co-founder and CTO, he will demonstrate how to use our system in the second half of the talk. So estimates vary, but the storage needed by images and videos, or what we refer as visual data, collected by various types of cameras across numerous different domains and industries, is expected to cross 80 zettabytes by 2025. It's naturally impossible for humans to pore over this data and find relevant information. However, the advancements in machine learning and data science techniques can help businesses across different domains extract valuable insights to cater better to their customers and improve their workflow. 4 years ago, back at Intel, when we started working on the design for an end-to-end visual cloud infrastructure to be used for machine learning on visual data, we spoke to ML researchers in academia and our own company. At the beginning, we only ever heard compute, DevOps, and accuracy-related challenges that people envisioned at the time in order to make machine learning a reality. Anytime we brought up data, we received feedback to the effect of data access can be hidden, training takes so long, or image data sets can really be discarded after we have trained with them, or we're not really worried about terabytes of data just yet. While all those challenges that people have been tackling still remain present and are being actively addressed, in the last 2 years, the conversation has shifted to include data and platform challenges. Now we hear comments and questions like, it's really hard to train on videos. Can I avoid fetching gigabytes of videos because I just really care about that 2-minute clip in it? Can I store multiple annotations or regions of interest per frame? They may be of different shape, not just rectangles. Or it keeps getting more advanced, like can I index feature vectors to restart where we left off, or find similar items to what I have? Or maybe I need to track and snapshot my subsets of data and in order to personalize my machine learning models, can I do that? And this by no means is a complete list. The challenges in data management are becoming more front and center, from actual storage and access to validating correctness, removing outliers, fixing bias. Today, we want to focus on one of those, the management of data itself. Let's first answer the question, why now? The reason we need to think or rethink our strategy now is that we no longer just stream this data. It's no longer just for display. We want to analyze it more and more. A valid follow-up then is, given the number of databases out there, why does visual deserve special discussion? Well, because images and videos can be individually large. Sometimes one image can be gigabyte size, and typically they occur in very large volume, like millions of images or videos. Databases typically tend to support operations like sum, average, count, which lose meaning for visual data. The equivalent and common operations there would be pre-processing tasks like resize, crop, rotate, and these can be performed on images, video frames, or the videos themselves. As common as these operations are across multiple applications, they can also be quite computationally expensive. So the complexity of operations is unique in this case. Visual data is also typically accompanied by a lot of metadata, because the metadata doesn't just contain information about that particular image or video itself, but also about the surrounding application, maybe regions of interest, features describing the content, and so on. So today, users basically have to adopt, the way out for them is to adapt and glue disparate systems that were never designed with visual or machine learning in mind. They typically insert data in some cloud storage bucket or maybe a distributed file system. They have to store their metadata in some database, which eventually may not evolve as fast as the application has been evolving. And then the pre-processing that we talked about that's needed for further analytics is then spread across these various components of the pipeline. Now, concocting such Frankenstein solutions and spreading the functionality across not only results in a maintenance nightmare, but also leads to a suboptimal one-time result. We have also discovered that the technical costs translate into businesses losing valuable time, resources, people, and competitive advantage when operationalizing their solutions, ultimately costing them millions of dollars. Also note that one thing we learned was while large software companies can develop and optimize infrastructure to solve this, there are numerous businesses out there who want to focus on their domain-specific value adds that are actually forced into building something or adopting something suboptimal to solve this problem. All these insights led us to forming ApertureData. ApertureData offers a unique database, ApertureDB, that has been designed for visual data. We call it unique because ApertureDB treats visual objects as first-class citizens by offering native support for images, videos, and bounding boxes that describe content in them. And of course, we also support pre-processing operations like zoom, crop, finding samples of videos, and augmentation operations through our interface. We manage the metadata information as a knowledge graph that can offer improving insights as your application keeps enhancing this metadata. This metadata is not limited to just describing the visual objects, but it can be anything about the application itself. We enable visual searches by storing the visual data besides this contextual metadata. Since feature vectors can be used to describe content in visual data, we also offer the capability to index and search feature vectors and also enable similarity searches. A result of this, and offering this unified, offering all of these functionalities behind the unified interface basically can save hundreds of hours of data platform engineering time, leading to faster analytics. Now, in an ecosystem of the various software layers, ApertureDB can layer on top of existing cloud or file system storage containing the visual data and then manage the various assets. It can respond to queries from machine learning frameworks, UI or visualization frontends, labeling frontends, and it can be made part of any analytics pipeline. The queries can be, adding, modifying, or searching the visual data or the metadata or the annotations. You can ask for on-the-fly pre-processing operations to be applied before you retrieve the images or videos. And you can, in fact, do more machine learning related tasks like taking data snapshots. And Luis will do a demo of some of these features shortly. Now, with its roots tracing back to Intel days, ApertureDB was always designed for scale and performance. In order to compare at least some of our features to what we've heard people do today, we set up a parallel system to approximate a portion of the functionality offered by our database. For visual queries that we run on a Yahoo, Flickr, YFCC 100 million image and video data set, we were up to 35 times faster, depending on the query complexity, and on an average, 15 times faster than that comparable system we set up. Since we can perform pre-processing on visual data near its storage location, rather than having to transmit it to the client and then do it, we actually can sometimes get unexpected and welcome reduction in network usage, since the common case is transferring a high resolution image or video or a video frame to a low resolution neural network or for thumbnail displays. So this actually is a pretty sizable benefit that often gets unnoticed. ApertureDB is currently deployed at a stealth biotech AI customer. Based on the feedback that we've received after a successful pilot with them, they have been able to save weeks of platform engineering time. They've already loaded over 1 billion metadata entities, and we are managing over 300 million images for their use case, and it's growing monthly. And they were able to achieve this with a lot more efficiently with their existing team. So at this point, I'll hand over the presentation to Luis, who will actually demonstrate with the use case on how our system works.
All right, let me share my screen. Hello, everyone. And let's go here. Let me know when you can see my screen so we can get started.
I can see your screen.
Okay, that's great. So the, give me a sec. How do I? This is not going away. Okay. Oh, there you go. So essentially what we want to show you today is one of the implementations that we have done using one of the public data sets that are out there. We choose the COCO dataset because it's a data set that has been used for multiple different challenges, and it also contains a lot of information surrounding the images. So this data set is exclusively composed of images, but there is a lot of metadata associated with those images because these images were processed and metadata information out of them were extracted, bounding boxes, position of bounding boxes, polygons of the bounding boxes, all this information surrounding the images have been made available. And we want to use this data set just to show you some of the functionality that we have. But of course, we support any other type of data set and much more functionality related, not only with images, but also with videos, with feature vectors that I'm going to be showing you a little bit of that functionality as well. And whatever user-defined information or metadata information that you would like to store for the processing of your application. But essentially, the starting point of this demo is that we have a pre-populated database that has the following information. So internally, we store all this information as a graph, and we will have a set of images here, and those images have two things associated with them for this particular data set. The first type of things is bounding boxes. So we have multiple different bounding boxes associated with each of the images. And each of those bounding boxes have information like the label that those of the object that they represent. They can be in bounding boxes corresponding to a horse, to a dog, to a cat. And the other thing we have, together with some information about the position of the bounding box, is for this particular data set, we have the segmentation information, which essentially tell us specifically which pixels belong to the shape of the horse or whatever is the label of that. So we have how much percentage of the overall area of the image corresponds to that specific object in the image. So we have that information, and we can model that information using our metadata store. And the other piece of information that we have associated with the main image is that we have a mask with the pixel level data of the segmentation of each of those images. So we have multiple of those images, each of those images with their own set of bounding boxes and the associated mask. So we're going to be playing a little bit with that. And the first thing we're going to be showing you about our interface is something that we are working right now, which is essentially an object model interface, so that you don't have to directly go and use our query language to type the queries, but rather using some higher level objects that will allow you to interact with the objects that you have on the database much more easily within your application. So that is essentially what we do here. We have a connector like any other database that you probably work in the past. You have to import some sort of connector. In this case, the connector, the module that has that connector is called VDMS, because the open source version of the project is called the Visual Data Management System. That is the project we originally started working on. And the connector for the open source version and our version, ApertureDB, it's the same connector. So the first thing we're going to be doing is establishing a connection to the server. This is fairly straightforward. We just go and connect to a server that is working on the same machine. And we're going to start using some of our object model interface that we have right now. So we will create a handler to deal with images. And one of the things that we would like to do is first run a search or a filter on top of those images. So we're going to instantiate a constraints object, and we're going to start adding constraints. So in this particular case, what we're going to be saying is, I want those images, but I want to constrain by the ID of that image being equal to this value. So we ran a search, and we essentially filtered those images based on that constraint, and we're going to be showing the image. So what's going on here is we go into the database, we run the query that will filter the image, all the images based on the particular ID, we return that image, and then we give you the option to go and display that image. So this is fairly straightforward, right? But we have the interfaces that allow you to do that very easily. And on top of that, you also have the ability to go and retrieve some of the, first retrieve what are all the properties associated with each of the images. You can run a query to retrieve that. You will get a list of all the different properties that those images have. And of course, you can just make a call and select a few of those properties and say, okay, I want to get the URL, the type, and maybe the license corresponding to that image because I'm interested in filtering by those. So you can see we get that information. So as I'm going to be showing you later, all our queries are JSON based, and the responses that you get are also JSON based. So you'll always going to have these JSON dictionaries to deal with the information very, very easily. So on top of just doing one constraint, you can, of course, this is a database with its query language, you can filter based on many types of constraints, right? So the next example that we're going to be doing is not only filtering by a single thing, but rather filtering by multiple things. And we can specify those constraints in this way. So knowing that each of the images have the properties of the width and the height, say we want to get only those images that are larger than 600 by 600. So we can express all that here and go and do a search into our database. When we do the search, we can specify, I want to limit. I just want the first 5 results because I don't want to show you thousands of images. So I'm going to limit this result by 5. That's another parameter you can use. And of course, go and display the images. And as you can see, I get multiple images. Let me run this so you can see the images more clearly. Let's rerun the query. So as you can see, you get 5 images. And in this particular case, these are images that were filtered by size. So these are all the images that are larger than 600 by 600, right? And one of the things that, that we can also provide as part of our interface, as Vishakha was mentioning, is this ability to deal with pre-processing operations. And in the case of images, or in the case of visual data, images and videos, there are a certain set of operations that are very common across many different visual applications. Those operations are things like doing a resize, doing a rotation of the image that it's useful for doing, for example, data augmentation, doing thresholding of certain values, even doing normalization, because you want to, those are initial steps that you want to run before passing those images through a neural network, for example. And those are operations that we provide as part of our interface, meaning that you can go and say, when retrieving certain images, I want to apply some pre-processing operations, and the database will take care of running those operations for you and will return you the final result of the image exactly as you want it and ready to be used for your processing pipeline. So what we're doing here is, as we were doing before, filtering these images, in this case by size, but it can be by any other property that you want. And we're specifying some operations. And in this particular case, we're going to do an operation resize. We're going to specify that we want a 224 by 224 image. And we're going to do a rotation, a 45-degree rotation. And this is another parameter that essentially tells you whether or not you want to resize the image. This is specifically to the rotation operation. You can check more on our documentation. And when running the search, we run the search the same way we used to. We specify the constraints. The other thing we're doing here is specifying the operations and, again, the limit. So we go and run this query. As you can see, we'll get these images that will filtered by size, and we get 224 by 224 rotated versions of those images. So all you had to do is express this set of operation, express the constraints, and this layer will take care of writing the queries, go into the database, do the filtering, and retrieve the images just as we want them, as you want them. As I was showing before, we also have the information about the bounding boxes in this specific data set. And in our interface, in our query language, bounding boxes are first-class citizens the same way that images are. So we can provide you with the functionality for you to say, okay, I want to retrieve an image, but I want to retrieve all the information of the bounding boxes associated with that image as well, right? So that is something that we can do. And given that we have the functionality to support that, we can write a layer that will allow you to not only get the images, but also get the images and display all their bounding boxes, right? So we can go and write the query, and all you have to do is specify that you not only want to display, but you also want to display the bounding boxes associated to that image. And given that we have the right internal abstractions, we can go retrieve those bounding boxes and put it here for you. So some of the images that we're getting before with all the bounding boxes are very easily produced for you for your use case or for your analysis, right? So of course, this is mostly something that we have been working on, this higher level interface, which have a rich set of functionalities, but underneath, essentially what all this interface is doing is using our query language, which is significantly more powerful at this point. And we're going to be showing you a little bit of how that works. So again, the starting point is this graph where we have all the information, and essentially the way our native query language works is based on JSON, and all you have to specify is the query expressed in a set of JSON commands that we have as part of our interface. All of them are pretty much documented in our documentation. So just to give an example, if we want to do the same thing that we were doing before, all we have to do is do a find image. We specify constraints, and we specify the list of, in this particular case, we can specify a list of properties that we want to get in return of that image. So all you have to do is, before we were passing the connector to the object model layer, but right now we just use the connector directly to say, here's the query, go and process the query, and as a response, I'll get a piece of JSON together with the image. So as you can see, I get the same image right now using the native interface, and I also get a piece of JSON that has all the metadata information that you retrieve as part of your, that you requested as part of your query. And in a similar fashion, if you want to specify the operations that you want to perform on top of the images, you just specify that as part of the query in JSON, specifying the type of operation and some of the parameters of that operation. So in this case, we're doing a rotation 90 degrees and a resize to 224 by 224. So you can see all of these operations. Essentially, what we're doing internally in the database is opening the image, decoding the image, running the operations that you request using our interface, and re-encoding the image in whatever format that you might want, and essentially return that image. And some of the things that we support is you can go and say, okay, I want the image, but I actually want the image as a PNG because my pipeline just supports PNG. And even though the image is originally stored as a JPEG, you can just go and run this, and you will retrieve and get a PNG version of the image. We'll take care of doing all the transcoding operations and giving the image whatever format that you want to do. So you no longer need to do any other extra steps on your application side. You can express all that as part of your query. The same way, the interface allows you to go and do constraints over multiple properties. I think we already went over that, but something more interesting that we would like to show you is how you can do even more complex queries and retrieve and do some further filtering. So initially, I was mentioning that some of the information that we have on the bounding boxes is that the pixel area of that object occupying in the image, in the overall image. So given that we have that information, we can express queries that essentially will allow us to run something like, okay, I want to retrieve all the images that I have on my database or in my data set that have a horse, but only those images where the horse is a significant portion of the image. Because say I want to train a model using horses. But those images where the horse is really far away and it's barely seeable, you can barely see it, maybe it's not something that is going to help my training. Even less when I go and resize the image to something much smaller, maybe that horse will become, I don't know, 10 by 10 set of pixels. So not really helpful for training. So we want to filter the data set based on those images where the horse are rather large. We can do that. So the same way that we have commands for interacting with images, we have commands for interacting with bounding boxes directly, and go and retrieve and filter those bounding boxes. So the query to express all this complexity of saying, okay, I just want the images where we have horses that are larger than 40%, can be expressed with two commands in our interface. So the first one is go and retrieve the bounding boxes, right, that have horses and where the percentage area is greater than 40%, and get those bounding boxes. And the second step that is going to happen within the same transaction is find the image associated with those bounding boxes, so that we retrieve the bounding box information and we retrieve the images associated with that. So we can express all that. Essentially, this graph traversal in this case is just a 2-level graph traversal, but we support any level of graph traversal that you might want to have. And on top of that, on top of retrieving that, we can apply a pre-processing operation. So we can say, I want those images of horses, but I also want to retrieve them in the 224 by 224 size. We're always using 224 as an example because that's the input size of ResNet, which is a common neural network for object detection, right? So we can just go ahead and run this query that will happen transactionally on our database, and you will essentially find those images of horses where the horse is more than 40%. Let me run this so you can see the result more clearly. And here we go again. So as you can see, you get all those images of horses where the horse is a significant portion of the image. And all the images are at the same size because they were resized on 224 by 224. As part of the JSON object that we get in return, we also have all the bounding boxes information that you might want to have. And the interesting thing, the other thing that we can do is not only retrieve these bounding boxes, but also retrieve the images that are associated with the original image that have all the segmentation information. So essentially what we're gonna be doing in this query is finding a certain image by ID, finding all the bounding boxes associated with those images, and also finding the image that is associated to the original image that contains the segmentation mask. So you can go and display all these. And this is another thing you can do. As you can see, it becomes a more complex operation in the sense that you're doing some exploration of the graph you have, but you can very easily model all these queries. And the fact that we have images and bounding boxes and videos and feature vectors as first-class citizens of the database allows you to express this in terms of operations that you want to perform on top of those. So in this particular case, we're going to retrieve all this information. So we're classic image of our horse, and we're also retrieving the segmented version of that image at the pixel level, indicating this is essentially that allows you to very easily interact with the visual data that you have on your database. We can have a very thin layer on top of our query language that will allow you to go and do more complex filtering and create custom data sets. So one common use case is that what you want to do is, as I was mentioning before, I want to retrieve only those images of certain tags or certain that have objects of certain tags or certain labels, because I want to build a data set specifically for that. And COCO dataset has a lot of images. Maybe I just want a smaller subset of images containing some specific objects that I want. And if I would have a tool that will programmatically allow me to do that, it would be great. And that is something that with a couple of hundred, even less lines of code in Python, using our interface, we were able to implement that layer that essentially allow us to do exactly that. So to give you an example, I will probably skip this one, but essentially what we did here is we created a build dataset function that essentially allows you to specify the name of the dataset and specifying the labels of the objects that you would like to filter on. So what we're saying here is I want to build a dataset that only contains furniture based on the COCO dataset. So from the initially hundreds of thousands of images that we have on the COCO dataset, we just want a smaller subset of them. And we only want those images where there is a dining table, a bed, a TV, and a couch. And we want 200 samples for each. And we want the minimal area of those objects occupying the image being 30%. So you just go, and as you can see here, I have my custom data set. I don't have any data set right now. We're going to go and build those. And we just go ahead and run this. And this will run in parallel because our database is fully concurrent, and retrieve those 200 images for each of the classes and place them in folders so that you can go and use them right away. So it took just 3 seconds to retrieve all those images in parallel. And that essentially created this data set here where we have furniture, we have a test and train. So for example, in the training part, we have 1 folder per each of the categories. And if my browser allows me, we can see some of the images that were associated to one of the labels. Look at that. Okay, so the last piece of functionality that we wanted to show you was related to this ability to deal with feature vectors. The same way that we enable the ability to deal with images and videos, you can deal with feature vectors, which are something that are very common across many visual applications. So feature vectors essentially allows you to run similarity matching and essentially go and find things that are similar to some other things. And one very simple use case that you can think of that is trying to find faces that are similar, right? So for this, I have another database that have a data set of images of a hike activity that we did at some point, and we have a bunch of feature vectors corresponding to each of the faces of the people that participated in that activity. So essentially, we can go and get a new image and say, okay, I have this face. I'm going to extract a feature vector for that face. And what I would like to do is go and find if my database have some elements that are close to that face, meaning that this face has been seen already as part of my data. So we have a command called find descriptor that will essentially go and find all the feature vectors that are close, and it will give me a label for each of those feature vectors that are the closest. And this is correctly indicating that the label associated with that feature vector is most likely Tom. And the other thing we can do is integrate that with what we have learned earlier, which is find images. So what we are saying is I want to find all the feature vectors of the faces of Tom, and I want to get all the images that are related to that feature vector, essentially returning all the images where Tom is present, right? So we have all the functionality. You can very easily express all that in a single query. At the same time, apply a resize, for example. And as you can see, we go and retrieve all the images in a database where they have a face that it's similar to Tom. So we have similar functionality with videos and with user-defined pieces of metadata that you can interact with in the same manner. So this is pretty much what we wanted to show you. On our website, we have more demos, but I think we can take some questions now.
Thank you, Vishakha and Louis. There's a couple of questions on the Q&A. If you could answer those, you can either answer them live or type an answer.
Okay. Yeah, I can take there was, I already answered one about, non-rectangular bounding boxes. So yeah, our plan is to add polygons and different shapes. Right now we have rectangles, as you saw in the demo. Then the other question is ApertureDB being offered as a managed service? That's our plan going forward. Right now, if you work with us, you can get, we'll give you a Docker that you can install and run for yourself. Extensible, I think the question, if I understand correctly, is more in the sense, can you add other forms of images? Yes. The difference that happens is, like, right now we've built in support, like we can handle PNGs, JPEGs easily, but typically now it's on demand. Like if we work with someone and they care about a certain different format, we can add it. Or the other general thing you can do is just store something as a blob. So you'll still be able to search and find. The difference would be all the pre-processing that Louis showed with the examples. That is for formats we understand. I don't know if there was any follow-up to that.
No, I think it looks like those were the two questions, right? So I just marked that they answered live. Yeah.
Yeah, and with the limitations, I would say, like, yeah, there are certain things we are building. Like we would like to have more connectors. Like Louis showed an example on how you could work with a PyTorch hierarchy. We'd like to build some more connectors and introduce these different shapes, regions of interest through our interface and host it on the cloud.
Makes sense. Thank you so much, guys. I really appreciate the talk. I actually had one quick question, maybe if we could take a minute.
Sure.
So I was just kind of thinking about your, so I was wondering, maybe two questions, mostly to try to think about how to put Aperture data in context. Would you consider yourselves a feature store for images or visual data? Because there has been a trend recently in the emergence of feature stores for machine learning. This started, a while back inside, large companies that had them. Like, good example is Uber, right? And now people are starting to create them. In listening to your talk, I wondered if I should think about your database as a feature store for visual data.
Yeah, it's not specifically a feature store, even though feature store is one of the functionalities that we support. And the reason why we chose to go that path is because our main focus was, we didn't start as a feature store. We started as a as a database for visual data. But very soon we realized that feature vectors is something that it's fairly common in many applications that rely on visual data. And we realized that usually when you deal with images and we deal with feature vectors, you interact with both of them as part of your application. So you select images based on the result of feature vector search, so that and that's the reason why we decided to just incorporate the ability to have a feature store within our database. And as I was showing you on the demo, that enables you to go and run a single transaction query where you do a similarity search using the feature store. And at the same time, you go and retrieve images associated with those feature vectors. And you can express all that complex search, which involves the similarity search, the filtering by constraints, the fetching the images associated with that. And on top of that, even pre-processing operations on top of the images behind a single interface. And in that particular case that I was showing you, a single transaction. So you can express all of that complexity in a single transaction. And the reason for that is because we realized that the interaction between feature vectors and images it's very strong. It's something that many applications use. And we thought that it was best if we just design a system that will take care of both of them behind a single interface.
I see. Awesome. Well, thank you very much, guys. It was a really great talk. I appreciate it. Does anybody else? I think we're actually a little over time. So if there are any final questions, please post them to the Q&A, but we'll give it 1 minute. And then after that, we'll thank the speakers.
Okay.
Or you can reach out to us. We are also on that Slack channel that Bill added us to. By all means, reach out to us. You can also write to us, team@aperturedata.io.